So far, the functions you have been playing with are functions which have one input, normally the variable x, and one output, normally the variable y. But why should there be only one input or only one output? Here we're going to be looking at extending the idea of a function to a situation where we have two inputs. So how is that going to work? Well, if we have two inputs, that means we're going to be playing with three variables, an x, a y, and a z variable. So we can visualize that as a three-dimensional setup. So we're going to be using the x and y's as our input and the z as the output. So we come up with something that looks like z equal the f of x and y. Well, we're going to have to see what that means. And what would the graph look like? Well, generally it's going to look like a surface. So this could be a typical, or maybe atypical, it's a bit of an interesting surface that represents this function of two variables. But let's start from the beginning. A function of two variables, also called the two-variable function, has two independent and one dependent variable. So it's of the form z equal f of x and y. F still stands for function, but now we have to introduce the third variable z as the output. So we start again from a three-dimensional coordinate setup with an x, a y, and a z. And then every time we pick an x and we pick a y, then that gives us a point of coordinates x and y. And once we use these coordinates into the function, that gives rise to a third point, which has z coordinate equal to f of x and y. So here is a basic example. So let's say we had the function z equal x squared minus y. So how do we compute this function? Well, the way you would imagine. So we have an x and a y, which are the inputs, and the z, which is the output. So let's say the inputs are 1 and 1. Then we put x equal 1, y equal 1, and you can easily calculate that the corresponding z is equal to 0. So we're dealing with the point in the x, y, z coordinate space of coordinates 1, 1, and 0. And similarly, if x is 2 and y is 1, you can do the math and it turns out that z is equal to 3. And then we can keep playing this game as long as we want. Okay? Now, in terms of getting the whole graph of function like this, well, that's something you'll have to wait until second year. We're just going to start getting our experience going, become familiar with these functions to see what they look like and how we can apply the calculus methods that we're going to be studying to these kind of functions. Now, in terms of features of these functions, most of them remain just the same in the sense that we can study them. Things like domain, range, and operations apply here just as they did before. For instance, again, let's have a look at these two functions. The function f is equal to x minus y over x squared minus 1. Notice that I'm using here the same convention in the notation that we've used for regular functions. So we can write f of x and y to denote the function, or we can write f to denote its output. It's, again, you have to play a little bit with both notations. Now let's see, what is the domain for these two functions? For the first one, of course, the problem comes from the denominator, so we don't want x to be equal to plus or minus 1. So the domain will correspond to any values of x and y, except when x is equal to plus or minus 1. For g, on the other hand, g involves a square root, so we have to make sure that the radicand is at least 0. So the domain will consist of all points x and y for which x plus y squared is greater than or equal to 0. What about the range? Well, just like for regular functions, sometimes it's difficult to figure out. For instance, the first function is not clear what the range is, and we may need to develop some further methods in order to figure it out. For the second one, on the other hand, is quite easy. We know that square roots can only be non-negative. On the other hand, by easily manipulating x and y, for instance, letting x equal to 0 and y be whatever number we want, we can make g as big as we want. So that means that the range is going to be any non-negative number. All right. What about operations? Can we add or multiply these functions? Yes, of course we can. We can add them by simply adding those two formulae and multiply them by multiplying the two formulae. And you can do the same thing with all kinds of other operations. Nothing really changes. But what about composition? Here we have to be careful. Let's see why. Again, let's use the same two examples to see what happens. Well, let's say I want to compose f and g. Well, I have to specify how I want to use g as the input for the next step. Remember that g takes two inputs and gives one output only. Well, where are we going to put that output? The way I've written it down, that means that I want g of x and y to be corresponding to the x input of the new function. So what that means is I'm going to use my g, so this function here, and I'm going to have to put it in wherever I see x, so here and there. So this x on top becomes the whole function g, and the x on the bottom becomes the whole function g, and then I have to square it. Similarly, if I look at f of x and g of x and y, now I have to take my g and input it where y is, so that ends up being in here. Okay, and then of course I can use the same idea if I want to compose the other way around. I'll leave it to you to work through these two compositions I'm showing and check that in fact they make sense. So you have to be a little bit more careful with the composition, but it's still done pretty much with the same idea in mind. One more concept which is related to two variable functions is that of level curves. So first of all, let's see what they are. A level curve or level set of a two variable function is simply what you get by equating the function to a constant. So you let f of x and y be equal not to the general variable z, but to a fixed constant k. So fairly simple concept. All you have to do is set your z, your output, to equal something. And again, let's go through an example. So let's say I'm looking at this function here, the same one that we saw before. So what I can do is I can let that expression on the right hand side equal a fixed number. So let's say 3 or -6. And what you end up with are level curves, right? So you can see that once you do that, we're back to just two variables, not two input and one output, but two variables linked together. How can they be linked? Well, a level curve may define an explicit relation between x and y. For instance, let's again look at our function and let's set that equal to 3. Then we can easily solve this function by isolating for y, and we end up with y being equal to x minus 3 times x squared minus 1. The only thing we have to be careful about is remembering that we don't want x to be plus or minus 1. So in this case, we have to actually add that to the information we have. But some other times, level curve may in fact define an implicit relation. Let's see, for instance, let's consider this slightly more complicated function. Well, if I set that equal to a fixed number, whatever that is, how am I going to solve this? There's no easy way, in fact, I don't know of any way, to actually solve explicitly for y. So this one can create quite a bit of puzzlement, and in fact, the curves that you're going to end up with from this kind of situations can be curves that are not actually functions. You can end up with something like this. I'm not saying that is the graph of this level curve I'm showing you. I'm just saying it could end up being all kinds of things. And this is something that, in fact, will have calculus implications later that we're going to revisit. Just keep that in mind. Sometimes the relation is explicit, sometimes it is implicit.